Hello everyone. So in this video I'm going to explain a circuit called R to R digital to analog converter. So here R and 2R means the value of the resistors. R is a resistor, 2R is twice the value of the resistor. As you can see over here, this is the diagram for R to R DAC where I'm using a 1K resistor and 2K resistors. 1K resistors are used in the series R and 2K resistors are used in the parallel R. And D3, D2, D1, D0 are the switches through which I'm going to apply a digital input. So I have taken a particular reference voltage here. That means if I connect that switch D3, D2, D1, D0 to reference voltage, we are applying that reference voltage as the input. That means we are applying 1. If it is connected to ground, means we are applying 0. So 1 or 0 as the input, 4-bit number as the input for the circuit, and it will convert that into the equivalent analog output voltage. That we are measuring in the voltmeter Vout. I'm using a op amp here as a voltage follower. So whatever the voltage is coming in the pin number 3, that will directly go to the output. So we can calculate the input voltage to the non-inverting terminal by using Thevenin's theorem. That can be applied. Thevenin's theorem can be applied, and we can measure the voltage. Now here we can calculate the output voltage by using this formula. That is Vout is equal to V reference A times D3 plus 4 times D2 plus 2 times D1 plus D0 divided by 2 power 4. That is 2 power 4 for 4-bit DAC. So reference voltage is selected as 5 volt in my case, and accordingly I have calculated the values. What is the expected output for this circuit? So as you can see over here, when all bits are 0, the output is 0. When 0001 is applied, it is 0.3125. When 1111, the last state is applied, I'm expecting a 4.6875 volt. The practical voltages we have to note down in the other column. Now going to the circuit diagram, and as you can see over here, this is the circuit is rigged up here as given in the diagram in the manual. We have used the R and 2R, that is 1K and 2K resistors in the circuit diagram. Now I'm correct. The inputs are given by using these switches, the digital trainer. So now it is 1111. So I start with the initial condition of 0000. So here this one is LSB and this is MSB. So I start with a 0001 initial condition. So I'll observe the output voltage. As you can see over here, it is around 0.24. That's what I'm getting. I'm expecting 0.31. So roughly I'm getting 0.24. So that is a practical voltage. Then for 0010, it is 0.56. I'm expecting 0.625. Fine, 0.56 I'm getting now. 0011, it is 0.93. I'm expecting 0.9375. I'm almost same voltage I'm getting. So when I change the inputs, as you can see, when I change the number, see now it is 0100, I'm getting 1.36. I'm expecting 1.25. So practically there's a small changes or variation. That is no problem. So when I apply say last condition 1111, I get 4.78. I'm expecting 4.6875. So this is R to R DAC. Thank you for watching. Okay, so this is second part of the same experiment, R to R DAC. In this case, instead of using switches as input, digital input, we have used IC7493, which is a mod 16 counter. So this is the mod 16 counter where pin number 12, 9, 8 and 11 are the outputs, which are used as the input for my circuit, as you can see over here. So when I apply a clock pulse, the counter will change from its state. It will change its state from 0000 to 1111, and those outputs of this are given to the input of my DAC circuit, and that circuit will accordingly convert that into the analog output or analog output. Now in this case, the reference voltage is actually not 5 volt. We have to measure the voltage at this point. Whenever it is high, at that time, what is the voltage that we need to measure? And that comes out to be around the 3.3 volt. So the reference voltage is taken as 3.3 volt here. So taking that reference voltage as 3.3, I have again calculated this column. Just this is actually theoretical value again, not practical value for the second case. So it is not same as before. Before the reference voltage was 5 volt, now it is 3.3 volt. So we are expecting this as the voltage. That is when it is 0001, it is 0.2125, and when it is 1111, it is very close to 3.3, that is 3.18 volt. Now I'm going to the circuit diagram. As you can see over here, I have used IC7493, and the output of that is given to the DAC. Fine. Now, when I apply a clock pulse through these switches, the counter output will change. This is the counter output, and that is given as input for my DAC, and I have to observe the output voltage in the multimeter. Now, when I apply a clock pulse, say I apply first clock pulse over here, I apply a first clock pulse, so my counter will change to a state of 0, 0, 0, 1. So that time the voltage is around 0.35. I'm expecting 0.21. I'm getting a bit extra. Now, when I apply one more clock pulse, the output changes to 0, 0, 1, 0, and the voltage is 0.52. I'm expecting a 0.42. I'm getting a bit more. So when I apply a third clock pulse, so output will change to 0, 0, 0, 1. So I get a voltage as 0.73. So digital input is converted into analog equivalent output. The same output can be observed by using a CRO. So as you know, it is given in the manual. The output will be in the staircase form. So for that, what you have to do is you have to change the clock pulse from monopulse to around 1 kilohertz. So when I apply a 1 kilohertz signal over here, what happens is, if I observe in the CRO, I get a staircase type of waveform. So this is changing, as in the manual is given like this. So as the input voltage is changed, increased, output voltage changes in the step-by-step fashion, as you can see over here. Thank you.